And so the question is, so we know the brain really always needs a constant fuel supply.
I want to start out very basic here. Is the brain, and especially in synapses, is it mostly using glucose as a fuel source? Is it using fatty acids at all? Has our picture of that started to change over time? What can you tell us about preferred fuel in the brain?
So the dogma has always been that the brain largely runs on glucose. In some simple ways, it's not that glucose isn't super important, but just an example of what you learn either as preparing to go to medical school or in medical school, that it's very important to try and keep blood plasma glucose levels relatively stable. And the reason it's always given is because the brain is so hungry for glucose. So you don't, and in reality, so an example I always like to give in seminars, if the sensitivity of the brain, if I gave you a shot of insulin and I could cause your plasma level glucose to drop by just a factor of 2 for the average human, down below, let's say I crossed the 50 mgs per deciliter threshold, right? Yep. So that's about 2.8 millimolar. Most humans would begin to manifest neurological symptoms. It's a fact, but it's a big drop. But you understand, you say, well, it's not much of a safety factor. It's just a factor of 2. So it is a big drop. And of course, that's unusual. The reason you won't is because you have a liver that will make glucose. Right? And so we've been endowed with organs to make sure it's kept as constant as possible given other constraints, right? So that is part of why the thinking about the brain is an obligate user of glucose. Now the question is, are there other uses? Now, one thing we strongly suspect as the field, and there's good data on this, is there is another source that we know this from therapeutics, which is for children that suffer from particular children that suffer from intractable epilepsy. And so this we call intractable is they're drug resistant, that they're nothing has seemed to helping them. The last last resort here is to go to a severe ketogenic diet. That's quite effective at something like 40% of those intractable cases. Those children really benefit from a severe ketogenic diet. So that of course is under a severe ketogenic diet, you generate a lot of ketones, usually in the liver. And the thought is that those are getting into the brain to be metabolized. And for some reason, there's now some bias, presumably, that's writing the imbalance of electrical inhibitory activity. Still not understood.
So still not understood. So ketosis is effective for many forms of epilepsy like that. Sort of implicit in that whole thinking there is, okay, if you're shifting the bias towards ketones when you do a severe ketogenic diet for that particular therapeutic application, that would imply that under normal conditions for most people, maybe the brain is biased quite heavily towards glucose rather than ketones. Is that the case?
Yes, I think for ketones, that is the case. Now, I just brought up the ketones as sort of an example, which I don't consider it the same because of machineries it needs, but it is a short hydrocarbon chain, a ketone. Now, but the longer ones, which was what we tend to consider fat, and what caught my attention is this sort of extreme sensitivity of the brain to interrupting fuel supply. So I gave you the example of insulin injection, as an Gedanken experiment where if I did that to you, I'm pretty sure I knew what would happen. But in addition, if you there are other ways to cut off your fuel supply. You could simply get strangled, and that'll cut off circulation. The same things happen rather quickly, right? And so the question is, so we know the brain really always needs a constant fuel supply.
From outside the brain, right? I'm sure the brain does have the ability to make stuff inside of itself, but what you're saying is you can't go that long without pumping stuff into the brain through the blood from outside.
So it probably is a bit of a hybrid vehicle, though, which is it isn't purely running on the traditional gasoline of glucose, such that there may be other systems that can run in parallel. And it's just that we don't quite know the rules of our hybrid vehicle yet, right? So, if you have a nice hybrid, Toyota Prius or something, well, you're used to using it, and you know how far you can get with its recharging system, et cetera. I'd say we don't know those rules yet. The evidence is accumulating that we really are a hybrid type of fueling system. And I would say the example I wanted to give is muscle is kind of like the brain, which is muscle is also very expensive to contract. And it needs fuel to do this job. And it has lots of things. If you go out and run a marathon, those muscles are going to do their darndest to make sure it gets all the fuel they need. And that it soups up the machinery to use that fuel, both to bring it in and to use it well. And muscle is famously adaptable. It's very flexible metabolically. It will use glucose, but it too is a hybrid kind of machine. Right. And one of the fuels it famously can use is fat. And I think I would say a starting mystery is, here's an expensive machine, the muscles in our body, and they're doing everything they can to make sure they can be adaptable for what kinds of fuel they have. And the dogma that had been around for 90 years was that, neurons don't have access to one of the pieces of fuel that muscles do, which is fat. And it seemed a bit of a conundrum that why would the brain have given up, since they're also very sensitive to all these things. They're very expensive. It seems like a good fuel source, so muscles have decided to use this.